My name is Yevheniya Nosyk. I'm a PhD student in the University of Grenoble, Alpes, and today I'd like to present you a tool which can be used to fingerprint the versions of DNS resolver software. So when we think about DNS fingerprinting, this kind of version-bound queries are probably the very first thing that comes to our minds. So the idea here is that we simply send a chaos class TXT request, and then in response, we get the version string. Now, the thing here is that DNS administrators can craft whatever responses they want to such a request, and they have been very creative so far. These are just some of the examples that you can find in the wild, not to mention the insults that you can see there very often. So, of course, you could try to filter out those very extreme cases and only keep those strings that look like valid pieces of software. But still, there is no guarantee that, let's say, somebody running bind 9 will not return you the version of unbound or the other way around. So all of that to say that this does not seem to be a very reliable mechanism to fingerprint DNS software. And ideally, what we'd like to have is some kind of tool that covers multiple vendors and versions, that is easily extensible and does not make any assumptions about software configurations. And this happens to be something that we have been working on since last year. So today I'd like to present you DNS software, which is a tool to fingerprint DNS resolvers. So essentially we had 4 things to do. We had to choose a software that we're going to test. Then we would execute some test cases. Then when we get the responses, we would need to convert them into the decision tree. And finally, we need to implement the scanner. So the very first step is what exactly do we want to fingerprint? So right now we support almost 700 instances of different recursive resolver software from 7 different vendors. The oldest version here dates back to 2014. So what we try to do is to include the most popular pieces of software, which are well documented, and those that have clear installation instructions. So of course, I realize that this is not an exhaustive list of all the resolver software running these days. So if you think there is something really important missing in this table, please let me know after the presentation. But I'd like to emphasize that for now, we're talking about recursive resolvers only. So once we're done with choosing the software, we need to think how to actually run it. And the easiest way really is to do it using Docker containers. So what we did is that we manually created almost all the Docker files. So more than 600 of them, but also we pulled some of the images from CZNIC Docker Hub repository. As for Windows, the easiest thing to do was to simply rent 3D PSS. So now that we have something to test, we should think what exactly do we want to test, right? What do we do? So as we're talking about recursive resolvers, the first thing that comes to mind is to really send a bunch of DNS requests and then to analyze the responses. So in this case, all our test cases are DNS requests. And then after all the queries are sent and we received all the responses, the bunch of all those responses is what we call a software signature. So then for us to generate DNS requests, we're mostly interested in those 2 sections, which is the header and the question. So starting with the header, we have a bunch of different fields here that can all be used to build DNS requests. So for example, if we want to send the recursive query, we will need to set the recursion desired bit to 1. or then if it's a standard query, then the opcode is 0. As for the question section, this is really what exactly do we want to ask. So for example, the queue name will be the requested domain name. The queue type will be, for example, A or quad A, and then the query class is internet, chaos, or something else. And then at the very end, when we receive the response, we parse the packet header and keep all the fields apart from the ID and the Z bit. So in total, we created 768 different test cases, which were the combinations of 9 different packet fields. So here we have 5 different flags, 4 different opcodes, 6 different classes. For now, we only have 1 resource record and 1 domain name that is under our control. So this is once again not an exhaustive list of all the possible types of queries that we could have sent. So we could have added many more resource records, many more different domain names with some various configurations. But at the same time, I do not want to overload this very first version of the tool. So we can always add more test cases later. So we also use our own domain name, as I mentioned, to send all the requests. So the main reason is that it's us who receive all the traffic. But also in future, if we want to add some particular subdomain with a particular configuration, then it would be very easy for us to do. So then for the testing phase, what we really need to do is that we start all the containers with DNS software. We issue all the test cases, then we kill the containers and save the intermediate results. And this process is repeated 30 times. So there are a few reasons why we need to repeat the whole process several times. So first of all, we cannot have just one signature per software, because with this little data, the machine learning algorithm that I will be talking about later simply cannot conclude anything. We need some more observations. And the second reason is that we may have some inconsistent results. For example, if there was some network failure while we were running the test, we can see some timeouts, but we will not see them during the other round. So basically, the idea here is to ensure that we have enough representative data for the next step, which is generating the decision tree. So considering that we have 15 million different request response pairs, there is simply no way we can manually create a bunch of if, then, else statements and classify the software. So that is why we need to adopt a more systematic approach. And that's why we have chosen the decision tree machine learning algorithm. So this approach is based on supervised learning, meaning that the model receives the signatures and the labels. And then it tries to learn the relationship between the inputs and the outputs. So another thing we need to think about is what exactly do we fingerprint? So is it only the vendor part? Is it the minor version? Is it something even more precise? So what we decided to do finally is to do fingerprinting at 4 different levels. And we created 4 corresponding models. So the first one will be the vendor. Means that we're not interested in the version string at all for now, only this leftmost part. So this is how the tree looks like. I'm not expecting you to read it in details. It's unreadable, but I simply want to show how the model makes the decision. And this process will look the same regardless of the fingerprinting granularity. It's just that the tree by itself will be different. So let's for now focus on the root node, ignoring all the child nodes. So we start with this type of query, which is of class reserved, and the opcode status. As I said, the domain name and the query type will always be the same, so I do not include them in the schema. Then, if the response to this query is not implemented and the only flag set is QR, then it would be classified as bind. If the response is anything different, then we go down the tree and check responses to other test cases. So to build this kind of tree, only 6 DNS queries were used, and we managed to distinguish all the software vendors. So I recall that at the very beginning, we need to issue as many as 768 different test cases, DNS requests, but only 6 of them were significant to distinguish all the vendors. So next we can go one step more specific, and this time try to fingerprint the major versions. I will not show any tree from now on because it will never fit the slides. But the key points here is that the more specific we want to go, the more queries we need to send. So that's pretty intuitive. And also, as we go more specific, we might not be able to uniquely identify every single version. So like in this particular case, some of the major versions of Technetium were not distinguishable. So here, once again, we go even more granular. That will cost us even more queries. So this time we're at 117 test cases to be issued. So finally, the fourth model that we built was used to fingerprint software up to its build or patch versions. But this requires us to send 149 different requests. And once again, not all the software is uniquely distinguishable. So the conclusion here is really like the more specific we want to go, the more we need to pay in terms of the number of queries. So the remaining step here was to really build the tool that can execute queries, load models, and then provide the result. So this is a simple Python program that takes the list of IP addresses to scan and the desired granularity. And based on that, the scanner will issue the needed number of queries, get the responses, parse them, unpickle the machine learning model, and provide the prediction. So this is how the output may look like. So in this case, we requested to get the version. In this case, we requested the major version. Here's a minor version, and finally the build version. Now, what can also happen is that you will get more than one label per IP address, like on the second line. As I mentioned before, not the versions are uniquely distinguishable, so you may get this kind of list in response. So that's how it looks like today. But there are, of course, many ways to improve the tool. So one thing is to add more test cases. So what we could do, for example, is to go to software changelogs so that we can see very precisely how one version differs from the other one. And then based on that, we can maybe create a specific test case or create a specific subdomain that could trigger those differences between software versions. Or similarly to that, we could go to user forums or issues to see what kind of unexpected behavior was mentioned by end user. Then another thing to check would be the RFCs, so the past RFCs, but also some of the ongoing work at the ITF, because those can give us, once again, even more ideas for building test cases. So there are lots of various sources from where we can get inspiration for new test cases. But at the same time, we could also remove some of the test cases. So, for example, if the results are inconsistent between different rounds when we test the tool, and we cannot explain those, probably better remove it altogether. The second problem is with timeouts. Like, we never know if the query was dropped somewhere on its way because of real networking issues, or it actually reached the resolvers that did not respond to this kind of query. Like, we cannot distinguish those timeouts. So once again, that is something we could avoid. And now the most important thing would be to test it in the wild. Like, what we really want to see is how the classification is done if we encounter some unknown piece of software or the one with some very specific configuration. So the main challenge here is that we do not have the ground truth data set for resolvers running in the wild, like IP address to software string mapping. But in any case, it's very important to test this tool on a real system, not just our toy example with a Docker file. So you're, of course, welcome to contribute if you wish to. I provide more details on GitHub, but essentially there are two ways in which you can contribute. So the first way is that if you want to propose some piece of software that can be tested, what I would need from you is a Docker file with all the instructions on how to run it, or maybe the link to the image on the Docker Hub. Then if you want to propose a test case, there is just one dictionary to update. But also if you do not feel like proposing anything, but just have an idea, you can still open an issue or write me an email. So then, of course, the next step would be to actually regenerate all the signatures, meaning that run 700 Docker containers. This is once again something that I can take care of. I can do it myself. You don't need to do that because in any case, I'm planning to maintain this whole thing regularly. Like, in general, I expect the tool to change quite a bit in the next 3-4 months, like based on the feedback I received today, and also based on this next steps that I'm talking about. And then, as I said, for now, it only supports recursive resolvers. But of course, ideally, it would be nice to have the tool that can fingerprint all kinds of DNS systems. So sortation name servers, forwarders, or how would it behave? Can we still fingerprint a resolver if there is a forwarder in between? So those are some of the questions that would be answered in future potentially. So just before I conclude, I would like to thank RIPE and CC for supporting this project with their Community Projects Fund. And that's all I have for now. If you have any questions, I'll be happy to take them.
It's Ray Bellis, ISC. I didn't see any reference to the old fpdns software written by Roy Ahrens and Jacob Schluter, I believe, were the authors of that. But I would suggest that you look into adding Q-types in your decision tree. I mean, for example, specifically, bind, if you send it a query for the mail B, RR type, will always send back not imp. And I think it's fairly unique in doing that. I would certainly suggest looking back at how the decision tree was built in fpdns, because I seem to recall the decision tree went up to as far as 64K possibilities versus your only 768. So there's definitely scope for a much bigger decision tree, I think, and getting more refined answers.
This is Jan Včelák, IBM. Thank you for the presentation. I really like the effort, and I look at the test cases, and I see like the test cases are a combination of all the flags for the header and the like query types and stuff. And I wonder if you considered any like alternative, like sending malformed domain names or like somehow generating these test cases automatically, and what the impact would be on the decision tree later?
So for now, it is generated semi-automatically in the sense that I was thinking what kinds of fields to choose for the domain names itself. I'm aware that there are some papers, some projects where they go even one step further in making it automatic, really like fast testing. Yes, I may consider doing that. Like basically what I wanted to do from the very beginning is to think every single test case very carefully so that I know what kind of responses can I expect. Then, of course, if you go with this approach, you can come up with 10 test cases per week, and it's never going to scale. So right now, I'm somewhere in between. So I'm still fully in control of what kind of fields I'm manipulating, but still trying to do it at scale.
Okay, thank you. That makes sense.
Hi, this is Mauricio Vergara from DigitalOcean. Thank you for your presentation. This was very interesting. I love the way that you were building use test cases for all of this. I was thinking that some of the methods that you've been using, it could be used as well for doing like a compliance kind of testing into software. I know that ISC has been trying to do some of that stuff on the completitude of everything that is related to ITF world, that they try to test things that they want to do, but maybe this can be used also as well to compare different software implementations to understand if they are behaving like the ITF rules are telling us. So thank you for that.
Yes, it's true. I have seen some work that was presented at the ITF this year. The scope is slightly different. We're not really looking for any vulnerabilities here or non-compliance with the standards. But it's true that if we have all this kind of data, like 15 million request responses, that's also one thing we can check.
Cool, thanks.
That's all for questions. Thank you very much for excellent presentation, Yevheniya.
Thank you.